Okay, today we will finish the Klein-Gordon part and then start with the Dirac equation. Well, the part that we will do now is the coupling of the Klein-Gordon equation with an electromagnetic field. Well, you have learned, well, an electromagnetic field we will give by giving 4 potential. It has a time part and a space part, and this is A0, AX, AY, AZ. Okay. Or otherwise, if you want to use the metric and bring the index down, then you have A0 minus A. Because of the minus 1 in the metric, you get that this where the value is the same, but there is this different sign. Now, which is, if there is an electromagnetic field, how do we couple it? Well, we use the same trick you have used in the Schrödinger equation. That means the minimal coupling, and the minimal coupling means, well, what is the analog of the energy of the derivative with respect to time goes into IH ddt minus E A0. E is the electric charge, and what is the momentum goes into minus IH, the gradient, minus E over Ci. So this is the minimal coupling scheme, and we can write this, if you remember, as a 4-vector notation, P mu, that goes into P mu minus E C A mu. Okay, and let's remember that P0 is equal to E over C, so all the right factor goes in the right place. Now, this minimal coupling scheme works. Now let's take the Klein-Gordon equation. That was this, and let's now turn on the electromagnetic field. Then with this substitution, you get that it goes into P mu minus E C A mu, P mu minus E C A mu, psi equal M0 C square psi. Now, on what is it, one can ask, on what is based these minimal coupling things? Well, it's based only on the fact that it works, but later on we will see also there is another reason related to gauge invariance, but let's say it works. So now if this is the operatorial form of the Klein-Gordon equation, if we replace the P mu, the derivative with respect to time for pi 0, and the derivative with respect to x for the other, what we get is the following things: 1 over C square I over H d dt minus E A0 square psi equal, let's bring this, the space part on the other side, and you get IH plus EC A square plus M0 C square psi. Now, so this is the form of the equation of the Klein-Gordon equation when you have an electromagnetic field? Well, you know that this part is related via its rotor to the magnetic field. How is related, to what is related this? Well, the usual convention is that E times E0 is the potential, the electric potential that you use to derive the electric field. The gradient of that V is the electric field and is related to the time component in this manner. Now, okay, so this minimal coupling works, and that would be sufficient, but there is another important thing that we should consider, that is gauge invariance. We know that the electric and the magnetic field don't change if we change, can I cancel here? You know that the electric and magnetic field, that after all are the observable quantity, don't change if we do a gauge transformation. The gauge transformation is something like this, that we change the gauge potential in the following manner. Where chi x is an arbitrary function. Okay, so this is a gauge transformation, and out of this transformation you get that E prime is equal E and B prime is equal B. I imagine you have done this in electromagnetic things, and I don't want to I don't want to spend further time. Now, as it is, the gauge fields are invariant. What we want is that also the Klein-Gordon equation must be invariant. If the minimal coupling is used, we could have used another coupling and other things, but what we want is that if the observable are invariant at the classical level, the invariance must remain also at the quantum level. Now, does this happen? So let's change, let me take, okay, let me write. Now, let's write with the metric so that we have everything down. Rewrite the Klein-Gordon equation in the minimal coupling scheme. And this is the gauge transform variable. Now, this equation does not seem to be invariant, because what happened is that the gauge field has changed, but nothing else. So this is not the one as before, because before there was I. Particularly if you go and replace I with the expression, you get G mu nu I H d dx nu minus E C A nu minus E C d chi dx nu I H bar d dx mu minus E C A mu minus E C d chi dx mu psi minus m0 c squared psi equals 0. Okay, and you see that the equation, this one, the previous one, the one without gauge field, had only this part. Now there is this extra part, so it does not seem to be invariant. Which is the way out? The way out is that under a gauge transformation, also the wave function change. And if you change the wave function in this manner, exponential minus IE HC chi of x times c of x, then if you insert there this expression, then you go back to the formal normal equation. Okay, why? Because you see, if you do this in the book, I think is wrong. The book it says there is a plus here, but there is a minus. I think is a mistake. So if this is the new equation, and you change also psi, you see that what happens if you change psi in this manner, you have this derivative that acts on this and breaks down a piece that cancels exactly this, and the same for this one. Okay, so under a gauge transformation, we have to transform the gauge potential in this manner, but we have to change also the wave function in this manner. Then the equation remains invariant, because if you now plug it in that thing, so what you get is exactly this equation. This equation that has the old gauge field and the old psi. This equation, this one, if you want, can be written in a compact form in this manner: IH d dx nu minus EC A prime nu IH d dx nu minus EC A prime mu psi prime minus M0 C square psi prime equals 0. So you see that this one, this equation, and this equation have the same form. That means they are invariant in form. What we have changed is the gauge potential and the psi, but they are not invariant in form if I don't change the wave function. If I do the following, this equation and that equation are not the same. There is this extra piece, so they are not invariant in form. So what you have to do is you have to change also the wave function. In which manner? You change the wave function in this manner. So this is how the wave function change under a gauge transformation. If you do that, then this equation becomes, it has this form, but it is basically equal to this. Means do the calculation, insert, and this extra piece gets cancelled by the phase of the wave function. So this is very important. In the book, there is some, I think, misunderstanding or mistakes in sign. Okay. So you see that the minimal, because we use the minimal coupling, we had to change, in order to have gauge invariance, we have to change the wave function in this manner. And you see, the fact that the wave function under a gauge transformation changed by a phase is a very important effect that is being measured. Most of you have heard about the Bohm-Aharonov effect. Okay, so the fact that under a gauge transformation the wave function changed by a phase is being experimentally detected, and you see it changed in this manner by a phase because we use the minimal coupling. If we had used another form of coupling, the wave function, in order for the equation to be invariant, had to change in another manner. Instead, it changed in this manner. Is everything clear? I'm asking because, I mean, this time is not enough to follow the book. So remember, with respect to the book, I have a different sign here. I have a minus. And this minus is crucial so that this equation becomes basically, once you insert the psi with this form, work out the phases, then these things cancel and you get back to this. Okay? Now, another, this is the last thing, is, well, is it possible with the Klein-Gordon, if we have, for example, an electric field, to do, you know, usually when you have an electric field and an electric field generated by a central potential, you can do separation of variable, at least in the Schrödinger equation. There is anything analog here? Yes, there is something completely analog here. So now we can start this small chapter that we will call central potential. And the separation of variable is in R and in the angular part, okay, radial and angular part. Now, it's very easy to see how to do. It's really completely analog to the Schrödinger case. Okay, so let's suppose we have our usual A0, and let's suppose the potential, the electrostatic potential, is the one that gives the electric field, is central, so it depends only on A. And let's take the case in which A is 0, so that we don't have any magnetic field. Then the equation of motion is the following. The Klein-Gordon equation is the following. And let's choose now a stationary solution. That means we are going to choose, so this is an ansatz we make, a solution that depends where the time and the space part are separated. So like we did in the Schrödinger case. So this is a stationary solution. So it is at a fixed energy, and there are not interference of waves with different energies. There is just one energy. Now, if you insert this expression here, the derivative with respect to t brings down an e, and the result here, this one is v of r, and what you get is e minus v of r square. Then you have this that acts only on this part, and left over it leaves this part, and then what you get is bring on the left hand side m0 c square c4. There is some problem with the c again here. No, it's okay. I multiply by h square c square Laplacian om c of r equals 0. Okay, so this is only on the space part of the wave function. This is the, if you want, this is what people call the time-independent or stationary Klein-Gordon equation. Okay, now let's go into, and we have to solve this equation. We have the fact that the potential depends only on r. So let's move from Cartesian coordinate to polar coordinate, r, theta, and phi. Okay, and then if we use polar coordinate, we can write this Laplacian in the form you know, and the result is, so basically and then I take this and bring on the right hand side, so the net result of this, especially in writing this part in polar coordinate, is the following: h square c square 1 over r square ddr r square ddr plus 1 over r square sin theta dd theta sin theta dd theta plus 1 over r square sin theta dd phi, all these applied on C of r, theta and phi, equal. Now I bring this part on the left hand side and I get E minus V of r square minus m square c square Okay, so when I said that this part depends only, I should have said here x, y, z, x, y, z. Okay, this one, psi of r, theta, and phi. Okay, so basically I've rewritten these in polar coordinate, is the first piece. I have changed the sign here. Well, it has a particular form, the Laplacian, this part. It has a particular form with a minus. Then I bring this on the other side, but there are some minus that compensate, and the result is this. Okay, now let's separate. Let's say I look for solution of this form. First, I look for solution that were stationary, the space part and the time part were separated. Now, in the function that depends only on the space part, I look for a solution of this form where the angular part is separated from the... So I am looking for not a generic solution, but a solution of this form. And now let's do the various, so if I look for solution of this form, let's see what happened. Actually, maybe a better way is the following. Instead of calling this psi of r, let's call this u of r. So I'm looking for solution in which the radial part and the space part is separated. Let me cancel here now. And let's see if there is a part when you work out, now you plug these into here, and you plug all these into here and into here, and work out the details like you did with the Schrödinger equation. If you don't remember, just go and see. And then what you do, beside plugging in, divide by the same, so you can divide, except in the region where there are 0, this wave function for 1 over psi, for 1 over psi. So first plug it in, do the calculation, but divide by the wave function, and also here divide by the wave function. Of course, if I divide here by the wave function in an exam, I said divide by the wave function, and this fellow cancelled, especially there, he cancelled. You cannot do that. I mean, there is an operator. So if you perform these things, the net result is the following: h square c square 1 over u ddr r square du dr plus r square e minus v of r square minus r square m0 c fourth equal minus 1 over y theta phi 1 over sine theta dd theta sine theta dy d theta plus 1 over y sine square theta d second over d phi square. And you see that in this manner we have really separated the radial part the left-hand side depends only on r, the right-hand side depends only on the angular variable. So what I have done, I have brought in this expression, but then this part that depends on r, I brought on the right-hand side that had, well, actually on the left-hand side or vice versa. And so basically insert this expression, these ansatz, and then divide by 1 over psi. Third, separate, if you can, the part that depends only on r from the part that depends only on the angle. You can. So basically the separation of variable works, but you have various things to do. First is to insert, do the calculation, but you have also to divide by 1 over psi, the full function. And in fact, the fact that you have divided by 1 over psi, the sign is here. You see there is a y in the denominator, and here there is a u in the denominator. As this part depends only on r, so this part is a function of r, and this part is a function of theta and phi. In order for them to be equal, they must be equal to a constant. So basically, this one is a function of r, but it has to be equal to a function of theta and b. So I say, well, look, this is a constant, and this must be the same constant, lambda. If you do that, then this single equation becomes two equations that are separated. They are not coupled, one to the other. And so basically put these equal to a constant, lambda, put these equal to a constant, lambda. The reason I can do that is because this equation tells me that a part that depends on r is equal to a part that depends on the angles, and that cannot be unless they are constant, each of them, and the same constant. So do, and write the first equation equal to that lambda, the second equation equal to that lambda. What you get is two equations. Let me write them. H square c square 1 over r square d dr r square du dr plus e minus v of r square minus m square c square minus lambda r square times u equals 0. This is the first equation. What I have done, I have put it equal to lambda, but I have also multiplied by u, because you see here there is u, but here there is no u. So I multiply by u, then I get a lambda multiplied by u. And there is also an r square somewhere that pops up here. I take the r square away from here, and then it appears in the denominator. I hope it's right. Yeah, I hope it's right, but check at home the various r square, okay? And then this other part is equal to lambda, and this other part, again, what I do, I equal to lambda, but then I multiply by the denominator, this y, this function y, and the result I get is this, sine theta d theta sine theta dy theta phi d theta plus 1 over sine square theta dy d phi square plus lambda y equals 0. But you see immediately that this part, yes?
There is no r square multiplied by e minus vr.
There is no r square here. Okay. What?
This expression is square.
This one square. Okay. So just, but check, because for sure there are other mistakes, okay? What my goal was to find out, to prove to you that it separates. Now, this part is nothing else than the one, or the operator of the harmonic, the spherical harmonics. So if these are the spherical harmonics, you know what is this lambda. This lambda, if you put h equal 1, is nothing else than L plus 1, okay, where L is an integer 0, 1, 2, 3, and so on and so forth. So I have determined which are the L. And then I plug it in this expression. The solution of these are the spherical harmonics. So the solution of these are the spherical harmonics that are labeled by two numbers, L and M, where L can be these, while M can go between L and minus L. Okay, so the solution of this equation is the spherical harmonics with lambda equal to this, just because the first term is the operator of the spherical harmonic. When you have this expression of lambda, lambda now is not a generic number, is this particular number, you plug it in here and solve this equation for R. So this is the well-known separation of variable things, and it works also for the Klein-Gordon equation. Okay, and well, somehow, you know, it's not a miracle that it works, because the Klein-Gordon equation, after all, once you is only the derivative with respect to t that is second ordered with respect to the Schrödinger. The Laplacian with respect to the normal coordinate is the same, so of course everything works out as before. It's only the derivative with respect to t that is second order in the Klein-Gordon. All the rest is the same. Okay, this you can find in the book. Huh? I am skipping a lot in the chapter of the Klein-Gordon. I don't work out all the examples that he does, pionic atom, Klein-Gordon in some strange potential. This is something that is useful for nuclear physics, so if you ever do any course next year on just nuclear physics, then most probably the lecturer will insert some of this potential, but that is not our goal. Our goal in relativistic quantum mechanics is to give as much as possible detail about the relativistic equation. And the relativistic equation, one is the Klein-Gordon, but we will not go into this detail with 20 lectures where I don't have the time, and this is really not in the mainstream of the program. Now, one last thing before going to the Dirac equation is the concept of pseudoscalar field. Now, when we did a Lorentz transformation that we will indicate from now on with something like this, so we know, for example, the rotation, the boost, all the things that we wrote explicitly is basically a linear matrix made of constant coefficient that depends on V and C that multiply the other variable. Of course, we know that the Klein-Gordon equation is Lorentz invariant just because these things is a Lorentz invariant, and this does not change. Okay, so the Klein-Gordon is invariant provided the wave function is a scalar. That means it transforms in this manner, and so this is a scalar. So if we assume that this change in this manner, that means it remains in the new wave function in the new points, is the same as the old wave function in the old point, that it means is a scalar, then this one is invariant, this is invariant, and the equation of motion is invariant. So the Klein-Gordon equation is invariant if you assume that it's a scalar. But you see, the equation is invariant also if you multiply by a factor, lambda, a constant factor. If you multiply by a constant factor, well, you see the constant, these remain invariant, the constant factor is getting out, and the new equation, this is a constant factor, the new equation is also equals 0. So we could allow for a factor to multiply this. Well, of course, we don't want that the charge density change, and the charge density is related to psi modulo square. You know, so this, as we don't want that the charge, total charge change, implies that the modulus of this is 1. Okay, so we can multiply by a constant complex number, like any wave function, of modulus 1. In this case, it has to be of modulus 1 because we want that the charge, the total charge that is plus minus E, is not changed under a Lorentz transformation. There is no reason a charge should change under a Lorentz transformation. So for sure, we have that the modulus of that is 1. Now, among the many transformation of the Lorentz one, there is all a family. We can change the velocity, we can change the rotation, and we develop all a family. But there is also one that is the identity. The identity is a particular kind, this is a direct delta. The identity is a particular kind of Lorentz transformation, after all, okay? Because you see, a Lorentz transformation preserves the distance. The only things that we know the Lorentz transformation has to do is to preserve the distance. Is in 4 dimensions, modulus the minus 1, the analog of the rotation. So the identity preserves the distance. So the identity belongs to the Lorentz group. Now, if under the identity we assume these things, if under the identity we assume that this change in this manner, if we do 2 times the identity, we get back to the same wave function, right? So if we do 2 times the identity, we go do this and then do again, we end up in the same. So lambda, in this case lambda enter 2 times, gets 1. Well, we knew that the module was already 1. Now, with the identity, if you do 2 times, we get back into the same things. Then lambda is this. That means not only it had modulus 1, but is actually equal to plus and minus 1. Sorry, I take it back. There is the identity that is important, but there is also another transformation that leaves the things invariant. Sorry, I take it back. I should have done a further step before. So there is the identity, and there is also the space reflection. The space reflection is the following transformation. x0 prime is equal to x0, and xi prime is equal minus xi. So this is the space reflection, and this is the identity. Now, the space reflection, does it belong to the Lorentz transformation? Yes, because it preserves the 4 lengths. So also these belong to the Lorentz group. It preserves the 4 length. Okay. Now, let's see if we do this, if we do a space reflection, and we get the psi x with the lambda that has to have this form. Now let's do another time. So basically we have done space reflection. Okay, x prime and x space reflection. Now if you do another time space reflection, you get the identity, right? So psi prime, do another time space reflection, lambda square, psi prime, psi double prime, psi prime, x prime. But this, yes, we have done 2 times, is the identity. So is lambda square psi x equal psi x. So I do 2 times the space reflection. The first time I do the space reflection, and I can get a coefficient that has modulus 1, because any Lorentz transformation can change the wave function by a constant coefficient. Now let me do 2 times the space reflection. If you do 2 times the space reflection, you get back into the same wave function. But if you do 2 times, you have multiplied by lambda square. Okay, so I'm doing 2 times, and this one now gets back into this. But as I have done 2 times, this is the same as psi of x. That means from here, I derive lambda equal plus minus 1. So under space reflection, the wave function can change in this manner, or it can change in this manner. Clear? Okay. So I repeat because it's a little bit delicate this point. The identity belongs to the Lorentz group because it preserves the 4 distance. Also the space reflection belongs to the Lorentz group because it preserves the 4 distance. The 4th distance you have to do the square of this, so it doesn't matter there is a minus sign here. Well, you can say, why you don't choose the 4 reflecting all 4 variables? Let's fix on this just because what I'm doing is just aimed at some consideration. So let's do the space reflection. We know that as it belongs to the Lorentz group, the wave function will change by a lambda. We know that that lambda from here has modulus 1. Now let's do 1 space reflection, I get a lambda. Now let's do 2 times the space reflection. If I do 2 times, I get back into the identity because I have to do minus of minus and I get back to xi. So if I do 2 times, I have to multiply by 2 things, but I get back to the original wave function. So I have that this one is with a lambda, okay, sorry. You understand the point. I'm doing 2 times. So I have lambda square. Actually, this is this. I do 2 times, and I get lambda square, but I stay with the same psi. Then this one, I know that if I do 2 times, I have to get back on the same wave function. So I get back to the same wave function as I get back to the same identity, to the identity. So from here, you get that lambda, not only modulus is 1, but lambda square must be 1. And that implies, so from here I derive that lambda square is equal 1, so lambda is plus and minus 1. So under a space reflection, the wave function can change in this manner. Now, those that change in this manner are called scalar field. They were already called scalars if they change in this manner, so it is consistent. This one that change with a minus is called pseudoscalar. Now, if you scalar is and pseudoscalar is related to the space reflection. It's not related to, so even if you change these, if you change, for example, x0 into minus x0, it's still a Lorentz transformation. If you do 2 times, it's still the identity. But that does not define a pseudoscalar, or sometimes they say is a total pseudoscalar. Some books use this notation. Total pseudoscalar, it means it is a it changes sign even when you change x0 into x0, or otherwise you can leave this invariant and just change thing. But the generic notation is we call pseudoscalar those that change by a minus sign when you invert the space coordinate. Okay, this concludes what I wanted to do on the Klein-Gordon. Just look in the book because this part are small part, like 1-2 pages, but scattered along the chapter of the Klein-Gordon. So I leave to you to find where they are. Just you write down the title, pseudoscalar, and then you find out minimal coupling, and you find where it is. You write down, as I did before, separation of variable, and you find where it is. Okay, so. Okay, this concept of pseudoscalar is quite important because there are particles like the pi 0 that are spin 0, so it's described by the Klein-Gordon, and also the pi minus and the pi plus. The other time we studied their charge parity, you remember, of these, the concept of charge parity of this. This time we studied the pseudoscalar. Well, all these are pseudoscalar. You can say why? Well, if you do this space reflection to be consistent with various decays that are present in nature, you have to give to this a pseudoscalar nature. Okay, so if you ask why, the answer for particle physics is always the experiment. The experiment tells you that these I don't know if you have been informed that tomorrow in Euler lecture room is one of these lecture rooms, the biggest one. Tomorrow morning at 8:45 there will be broadcast of 2 seminars from CERN. You have heard about that? Okay. If you have time and you don't have any class, I advise you to come, because there are these different kind of rumors. Some say that the discovery of the X will be announced. Some say that no, it will be a preliminary thing. But still, if they discover the X, and you know the X is a scalar particle, so now you have all the equipment. It means you can say in your life, if tomorrow they announce the discovery of the X, well, you know, they discovered the X just after I finished learning about the spin 0 particle, and it would be the first spin 0, you know, scalar particle that, I mean, plays really a fundamental role in the sense that is, while pi 0, pi plus, pi minus are composite particles, the pi 0 is made of 2 quarks, and the quarks are combined to give a spin 0. Okay, instead it seems, at least in the standard model, that the real fundamental not being made by other particles, spin 0 particle, the only one in nature is the X, and personally I don't think it exists, but maybe tomorrow I will be. Most probably the bump they see in the cross section is due to some bound state and so on. Okay, now we start a chapter, please. Now we are going to the Dirac equation. If you now want a spin 1/2 particle, the equation is the Dirac one. Okay, first we will start formally, and only later on I will prove to you that it describes spin 1/2 particle, but we will describe the Dirac particle. Now Dirac did not have in mind the Dirac equation. Now Dirac did not have in mind to describe a spin particle, but we will see at the end that the equation that this equation describes a spin 1/2 particle, but he did not have in mind that. He had in mind to write a first order equation in T, okay, with a probability interpretation for psi. We have seen that in the Klein-Gordon it was second order in T, and was that forbidden probability interpretation, because if you remember, the rho was done over psi modulo square minus a chi modulo square, so there was this minus sign, and that it was not possible to give a probability interpretation. And it was because originally it was not in a first order formalism. Even when we brought into a first order formalism, with that 2-component formalism, still we did not have a probability interpretation for psi, because the 2 components were phi and chi that combine in these strange things with this -1. So Dirac wanted first order equation in T, so that most probably it would have as a consequence a probability interpretation for the wave function. Second, Lorentz invariant or covariant? Well, if from the beginning you had first order in T, then to be Lorentz invariant you have to be first order also in X. Okay, because remember the Lorentz transformation mix T and X, and if it is first order in X or in its derivative, it must be first order. In fact, look at the Klein-Gordon. Don't look in that other second formulation. In the first formulation, it was second order in T and second order in X. So it must be first order in X and first order in X. So Dirac basically, that is what he wanted. And the result he got is he got an equation that describes spin 1/2 particle. But we will get there in few lectures from now, okay? Have you already done some exercise with the person who does the tutorial? Not yet. What did you say? The tutorials are when? Starting this Friday. Okay. I think he will do some tutorial on the relativistic part, relativistic Lorentz transformation, and only later on there will be some tutorial on the Klein-Gordon and on the Lorentz. Okay, so I leave to him the problems because I have a lot of material to cover. Now, so that is what Dirac wanted. First order in T, Lorentz, okay, so these imply first order in X. So in order to have that, he wrote an equation, X psi T equal HCI, and then he multiplied, he wanted first order, so he multiplied by some coefficient, alpha 1 ddx1 plus alpha 2 dx2 plus alpha 3 ddx3 psi. Oh no, sorry, he can put a constant term, so let's put plus beta m0 c squared. You know, this is the most general first order equation that you can have, first order since there is only the first derivative. Now, and the mass, because we have a particle with mass, this is the most general. And then he said, well, let's take more general as possible. Let's suppose that is alpha 1, alpha 2, alpha 3, and beta are matrices, and that this psi is a multi-component vector. That means let's suppose that this psi is a psi 1, psi 2, psi 3, blah, 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 psi n, and that alpha 1 or alpha I and beta I, beta R, square matrices n by n. This is the most general first order equation that you can write. You can say, maybe I could put a coefficient here also, yes, but you know, if you want to have the correct non-relativistic limit, you know that you have to end up in the Schrödinger equation, right? The Schrödinger equation has this form here. So let's keep that as in the Schrödinger equation, and let's have as much freedom as we can, but not really exaggerating. So basically, this is the most general form for a first order equation. Now, why he wanted to be matrices? Not only to be general, but let's say this has to be Lorentz invariant. Inside the Lorentz group, there is the rotation group, right? The rotation group acts only on the space part, and it must leave this invariant, right? Let's take only the, inside the Lorentz group, let's take the rotation invariant. Then this part must be invariant. But we know that the derivative with respect to x1 under a rotation goes into a combination of derivative in the other direction, the same this, the same this. Then, in order for this to invariant, the alpha 1 must change into the alpha 2, into the alpha 3, and so on and so forth. So that means these objects either are vector or in general they are matrices, okay? That means they are not numbers. If they were numbers, fixed numbers, then these would not be rotation invariants and so also not Lorentz invariants. So these are not just numbers, they must have another nature. And Dirac suggested that they are matrices. Somehow, you know, it is like the following. Imagine the rotation. In the rotation, you have Lx, Ly, and Lz, the generator, right? And if you do a rotation, you know that Lx goes into Ly or Lz if you do a rotation. Don't look at them as operators. Look at them as vectors. Okay? If you look at them as vectors, the three angular momentum. The angular momentum change under rotation because it's a vector, so like all vectors, it changes under rotation. One goes into the other and into the other. But at the same time, we know that these in quantum mechanics are realized as matrices. Okay? So anyhow, these cannot be fixed numbers. They have to rotate one into the other. So the other things is that, you know, well, okay, I think this, there are various, I mean, one has to be convinced why these cannot be number, because this has to be Lorentz invariant, so these have to rotate into each other, so they must have some structure. And Dirac made the hypothesis that the structure they have is that they are matrices. Now, if they are matrices, what we can do is, as these are matrices, they have index, they have two index. So we can, for example, and also these has an index 1 to n. So let's put an index sigma to indicate that there are many. This is a matrix acting on a vector. So we can put two index sigma tau. Also on beta, beta also is a matrix. So let's put two index sigma tau. And it will act on this column tau. Okay, so this is the notation if you want to highlight the matrix and index structure of your things. And you know, all these, if you want to write in a form that is as similar as possible to the Schrödinger equation, because this first term is already as a multi-component of a Schrödinger equation, then you can write all these as an Hamiltonian. Usually it's called Dirac Hamiltonian. I don't know why this guy wrote F. In the book you find HF. F may be for fermions, he never explained. Usually this is called Dirac equation, Dirac Hamiltonian on psi, on psi. Okay, so the Dirac Hamiltonian is this, is all these operators. All these operators, including this, is what is called Dirac Hamiltonian. Now, what do we want? Because we have not specified alpha, we have not specified beta, and so on. So we want to find, is there any specific form of alpha and beta, or are they generic? Well, what do we want? We want that, at least for the free waves, we want that the usual energy-mass relation is satisfied. So we would like, there are various things, let's write them here. What do we want? We want that somehow, out of that equation, if we plug in solution carrying energy and momentum, we want that this is satisfied. Second, we want that a continuity equation exists, so that means we want that d rho dt is equal to the divergence of J, continuity equation. The continuity equation, and you know, here we wanted the probability interpretation. Third, you want the probability interpretation, so there was already this requirement, and the continuity equation, not only we want a continuity equation, we want also that the rho in that continuity equation has a probability interpretation, and the other is the Lorentz invariance. So continuity equation parse probability interpretation, and third, Lorentz invariance or covariance. What does it mean? Invariance, it means it remains the same. What does it mean covariance? Covariance, it means it changed by a matrix that you can drop out. So for example, if you have some vector equals 0, then that this equation is covariant. It means that under a Lorentz transformation it changes in the following manner. Okay, but it has only a coefficient in front that is a matrix. Then in that case you talk about covariance of your equation. But okay, so these are the requirements he wanted on this equation. And let's see now what happened with this requirement. Okay. In order to satisfy the first things, we want that if we apply the derivative 2 times, let's apply the derivative 2 times. So that means EH, it becomes minus h squared, d psi sigma dt square. And we want that if we want that this is satisfied, then we want that this becomes minus h squared c squared lambda squared plus m squared c to the 4th on psi sigma. We want that that relation is satisfied, but that relation must be satisfied. If it is satisfied like that, it is satisfied also at the operatorial level. But at the operatorial level, it means you can apply a psi and get this, and any psi. Here we have n psi because they make a multiplet. So now the derivative 2 times with respect to minus h, the derivative 2 times with respect to t is e squared. So basically this is e squared on psi sigma, and this is pi c squared plus m0 squared c squared psi sigma. Okay, so you see from this equation we want that if we derive 2 times we get this equation. Why we want to get this equation? Because this is the operatorial version of this, and if this is true, it also is operatorial version. Once you give the correspondence rule must be true. Okay, so the requirement was this, but this implies that also the operatorial version is true. The operatorial version makes sense only if you apply to a wave function, so it means this. But this, what does it mean? This means this, because I take as E, as operator E, the minus I ddt, and as operator P, H, C, derivative with respect to xi, and so on. So you see these that we want to hold imply this. Okay, so let's stick to this. That is the first requirement Dirac wanted. This is a crucial point. He wanted that this equation satisfy this. Well, let's now start from this. Let's do 2 times the derivative. So this is what we want to achieve. That each component, whatever is the equation that Dirac postulated, satisfy this, because this is the mass energy relation. So let's do here, let's apply here IH ddt. okay, so that I get 2 times the derivative. So let's see. I get minus h squared, the second derivative of c sigma dt equal, then I have h c I alpha I ddxi plus beta m0 c square, and then I have I h bar d c d sigma, I h bar, okay, this one. I've applied the time derivative, and it goes and acts on this, the time derivative, okay? But now, this one, what do? I take this object, I know that the first order derivative is equal to this, so I replace this with the first order derivative, that is this object. You understand what I've done? I've applied the first order derivative, and I go on. Here I get second order derivative, then I get this piece, but here I don't get any more psi, but I get first order derivative. The first order derivative, if I look at this equation, is equal to this quantity. So insert, okay, you have to insert that things with the alpha and beta and so on and so forth. Let me cancel here for the moment, otherwise I don't know where to go and write. So you get a lot of now, so I take away the time derivative and replace with these things, with alpha and beta. What you get is the following things: minus h squared, the second derivative of psi respect to t. Let's take away the index for the moment of the component. Then I have to be careful because here I call alpha I, here I apply, I get things, but I will call the index j in order not to mix. And what you get a lot of combinations that are minus h squared c squared sum over I and j, alpha I, alpha j, plus alpha j, alpha I. Remember that they don't commute because in general they are metric, so I take these things divided by 2. Then I have the second derivative of psi with respect to xi, with respect to xj, plus h m0 c cube over I, sum from I from 1 to n, alpha I beta, plus beta alpha I, the psi dxi, plus beta square m square c square psi. Okay, so basically I've inserted here this expression, calling this index not I but j, and then I have to do all the product. If you do all the product, you see, you have to be careful because you get this expression. Okay. Now, we want that this equation, that is the second order equation, we want that this equation be this. Right? But if you want this equation to be this coefficient have to satisfy some relation. Well, first of all, where the b square come from? The b square come from because when you take here there is a term with b and b gives me this. Then you have b and alpha and you get these things. But you know, you get 2 times because you get the beta here multiplying the alpha there, and then you have the beta here multiplying the alpha here. Okay? Then why there is alpha mixed? Here is the alpha I, and it goes and multiplies the alpha j of these things. But you have also then the alpha j of these multiplying these things. Okay? So you have 2 times the things. Okay, so it has to be this. So do as an homework, work out as an homework that one, okay? That means So the homework is start from the Dirac equation, impose this relation on each component, and see if you get this. I can write down for you from the book. So if you want a more compact things, starting from equation 2.5 on page 100, derive the first equation on page 101, derive the first equation that is on page 101, using the fact that each component must satisfy, sorry, cancel just 101, stop it when I said 101, all the rest cancel. So start from 205, equation 205 on page 100, and derive equation 101, the first equation on page 101. Okay, now if you want that this object is this, if you want that this object is the Klein-Gordon equation, there is no other way than the following one. This equation will become this. The first term is okay. But then we have the second term, and the second term, you see, these things is the Laplacian only if the alpha I, alpha j satisfy this relation. Alpha I, alpha j plus alpha j, alpha I equal to delta ij, but all these are matrices, so you have to multiply by the identity matrix in m by n. This is the identity matrix in m by n. And if you have this relation, then the 2 cancel the 2. Only the coefficients that are equal remain equal, and you get exactly this term. Then, on the right-hand side, do we have first-order derivative? No. So this must be 0. So the second condition is that alpha I beta plus beta alpha I is equal 0. The third is this. This is beta square times this must be equal to this. So we need that beta square is equal to the identity. But it's the same, you see, if you take I equal j here, you get alpha I square plus alpha I square equal 2 times 1. So basically, you have also alpha I square is equal the identity. Okay, but this is already contained here. So the three new relations are this. These are the conditions for this strange equation to end up and be like the Klein-Gordon equation if you do second order. Well, these are matrices, and you know, if I is equal from j, this is 0, right? And the same here, we have 0. So people say that alpha and beta matrices of Dirac anti-commute. What does it mean? It means that if they are different from each other, means the index are different, then this is 0, and so they anti-commute, right? They anti-commute because this is equal. So if I is different from j, what do I have? I have alpha I, alpha j, plus alpha j, alpha I equals 0. But this means alpha I, alpha j is equal minus alpha j, alpha I. So they anti-commute, right? The same for beta. From this one, what do you get? From this one, you get alpha I beta plus beta alpha I equals 0, but this implies alpha I beta is equal minus beta alpha I. So both the alpha I and the beta with the alpha are anti-commuting, but only if the index are different. So when you hear the sentence, the alpha matrices of Dirac anti-commute, yes, when the index are different from each other. Now, I cancel the equation. If you remember, I had minus IH tip psi dt equal alpha I ddx psi plus beta m 0 square c. Let me just get the right one. Okay. Right. Okay, now the alpha, this was what I call the Hamiltonian, the Dirac Hamiltonian. This has to be Hermitian, okay? Why? Because you want that the evolution is Hermitian, is unitary. And so the operator, the tags must be Hermitian if you want that the evolution is unitary. So for this to be Hermitian, the alpha I has to be Hermitian because I, ddxi, is an Hermitian operator. So you want that alpha I are Hermitian. And the same for the beta. So these extra condition, we have to add them here. Let's add them here. Alpha I dagger equal alpha I, beta dagger equal beta. These are extra conditions that guarantees the hermeticity of the H. And often I ask why the H in the Dirac equation has to be Hermitian. There can be, you know, one problem. I just give two problems in the final exam. And one problem might just be a set of simple questions, like why the Dirac equation has to be Hermitian. I mean, I want the physical reason why it has to be Hermitian. It has to be Hermitian because otherwise the evolution is not unitary, like in the Schrödinger case. Okay, so it might be, I have not figured out yet. What I will do anyhow is the following. Even in the second set of homework, whatever is the number of problems, I will give grades so that the sum is like in the previous set of homework 50. So that the two homework put together, those who got maximum grade 50 and 50 is 100, right? And the same I will do for the final exam. The final exam, each problem 50, so the total is 100, okay? In that manner, you know, the homework is only 30% of the final grade. For me, it's easier in that manner. I have 100 points from the homework, 50 and 50. You understand? So getting 30% of that, it means I will give 30 points from the total amount you got. And the final exam, two problems, 50 points each, I will have 100 and I have to take 70% of that for the final grade. You understand? So even if there are more than 5 problems in the second set of homework, the total point will be 50. I will distribute the points so that this 50, you understand? Okay. So it's easier because I don't want to make mistakes. Okay. Now, let's see, now that we have this relation, let's see if we can, so these are the conditions that we have. Dirac started very general, but in order to satisfy many of the things, he ended up that his matrices, alpha and beta, of his first order equation have to satisfy this. Let's see if we can derive some extra things from this. Because, now we want to get a specific form. And we will get a specific form. Well, first of all, now we will prove that these matrices have trace 0. This is easy. Well, let's start from the second one. Alpha beta plus beta alpha e. Okay, we know that this is 0. Let's multiply on the left from beta. Beta alpha e beta plus beta square alpha e equals 0. I've multiplied by the left for beta. This is 1. So I have beta alpha e beta plus alpha e equals 0. Now let's take the trace. Trace of beta alpha e beta plus trace alpha e equals 0. Now, you know that the trace is cyclic. So this is equal to trace beta alpha e plus trace alpha e equals 0. But this means trace alpha e, this is the identity, plus trace alpha e is 0. So it means trace alpha e is equal minus trace alpha e. That means this must be 0. Note that this property does not change if you transform the alpha. Let's suppose we transform the alpha in this manner. Alpha, whatever is the alpha, u minus 1. Now we take the trace of alpha prime, which is the trace of u alpha u minus 1. And this is trace u minus 1 u alpha using the cyclic property of the trace. Okay, everybody is familiar with the cyclic property of the trace? Okay, and then these cancel and you get trace alpha. So you see, even if you do a transformation on the alpha, you get. Now let's see if the beta has trace 0. Let's start again from this. So I have proved that alpha have trace 0. So let's add them here. Trace alpha e is 0. Now, let's multiply this relation by alpha to the minus 1 from the right. So alpha I beta alpha I to the minus 1 plus beta alpha I to the minus 1 equals 0. This gives me 1. I have alpha I beta alpha minus 1 plus beta equals 0. Let's take the trace. I have alpha I beta alpha minus 1 plus trace beta equals 0. But this one, I use the cyclic property, it becomes alpha minus 1 alpha I beta plus trace beta equals 0. This goes away, and what you are left is trace beta plus trace beta equals 0. So trace beta equal minus trace beta. That means this is 0. So, second property. These matrices have trace 0 or they are traceless, people say. Another thing, you see that the square is 1. When the square is 1, not the modulo square, the square is 1, it means the eigenvalue can only be plus or minus 1. Okay, that is very simple to prove. I leave you as not one of the homework, but just a simple things prove that if the square of a matrix is 1, then the eigenvalue of this matrix are plus and minus 1. But if the trace is 0, the trace of alpha is equal to the trace of beta and is 0. The eigenvalue are 1 and minus 1. It can only happen if the dimension of these is even, right? It can only be 1 and minus 1, the eigenvalue, from this property. The trace is 0. That can only happen that summing 1 and minus 1 if it is even. So that means n, the dimension, is an even number. Now, let's now go and choose. The eigenvalue are plus and minus 1, the trace is 0, the dimension is even. So which is the smallest even dimension? 2. So let's start with n equal 2. We are looking for matrices that have trace that satisfy that property, anti-commute, into that have dimension 2. The eigenvalue is 1 and minus 1. The only one who do this are the 3 sigma matrices, sigma 1, sigma 2, and sigma 3 of Pauli. But these are 3, and I need 4, because alpha I goes from 1 to 3, and beta, so I need 4 matrices, and I have only 4, I have only 3. So n equal 2 cannot be the right number. Next even number is n equal 4. So n equal 4 is the smallest number that satisfy the all that set of conditions. And which is the solution of that? Well, you know, remember that the sigma matrices, when the index are not the same, exactly satisfy this. You know, the anti-commute, the sigma matrix is anti-commute. So playing with the sigma matrix is actually easy to build the alpha in 4 dimensions. The result is this: alpha is equal to sigma I 0, 0, and beta is equal I, the identity, 0, 0, minus I. This is the smallest solution of the Dirac equation. Not solution in the term of wave function, but in the term of the matrices. So these are called Dirac matrices. There are these and there are others, but you see, you build them out of the Pauli matrices. If you want them written in an explicit form, we can do. So alpha 1, we have to use the sigma 1, and it will be 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0. This is alpha 1. Alpha 2, 0, 0, 0, 0, 0, 0, 0, 0, minus I, 0, 0, minus I, 0. And alpha 3 is 0, 0, 0, 0, 0, 0, 0, 0, 1 minus 1, 0, 0, 1 minus 1, 0, 0, and beta is 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, minus 1, 0, 0, minus 1. Okay, so this is the smallest realization of the Dirac equation, and you can check that the anti-commute, that they have all this property. Okay, we stop here. Thursday we will go on with the Dirac equation, and I don't know if we will have time to do higher spin equation, but the higher spin equation, like equation for spin 2, spin 3 half actually, spin 1, spin 3 half, and so on, are things that you will do in more detail when you do the particle physics. So I think for this course we will work out many details of the Dirac equation, but we will not go to higher spin equation, okay?